My name is Sergey Levine, and I'm going to talk about embodied implicit scene understanding. So, when we think about how machines can understand the world, perhaps it's most natural for us to think about it structurally, in terms of building up useful representations, like geometry and physical properties, and then utilizing them to perform downstream tasks. So this is a very reasonable way to approach this question if we think about scene understanding kind of as engineers. Because as engineers, we're taught that engineering problems are more manageable if they can be reduced to the right abstractions. In fact, arguably this approach to scene understanding is as old as computer vision. If you think about perception as inverting the physical process that gives rise to images, essentially kind of an inverse graphics, that's perhaps one of the earliest ways to approach computational perception. And it's a very reasonable way to start thinking about the problem. But I think some of the evidence that we have in recent years suggests that to enable capable autonomous machines, a different approach might be more effective. The trouble with this very explicit way of thinking about scene understanding is that it requires us to manually specify the right intermediate representations. And while it might be straightforward to do this in simple, idealized environments consisting of simple, rigid objects with smooth faces, the real world is never quite so complex. And perhaps this is why the most successful methods for perception, and increasingly the most effective methods in robotics, actually get rid of manual specification of abstractions and instead utilize end-to-end training to acquire the right representation for the job. So you might take a large data set, a largely undifferentiated high-capacity model, and then use it to learn to perform some very complex tasks. And while we might say that such an approach perhaps loses some of the interpretability or maybe even some of the generality of more explicit methods that specify the representation, in practice it tends to work quite a bit better. Now, we might be tempted at this point to think of these kind of end-to-end approaches as being more narrow and task-specific because they're typically trained on a task. So we could imagine that the world works like this, that there is a kind of the world of Platonic ideal representations, which we know and which we define ourselves, and then the world of end-to-end learning, where the end-to-end world is task-specific and these idealized representations are general purpose. But here, too, recent evidence suggests that this may not quite be the case. So we know, for example, that in computer vision, if we take a large high-capacity model and train it on a large data set, and then pull out the features from that model, those features can actually be useful for many other visual perception tasks. Somehow in the process of learning this seemingly specific task, this model actually acquired what we might call an understanding of visual scenes. So end-to-end systems that can actually learn general concepts. What this brings us to is that there are kind of two differing views of scene understanding. There is a classic view that says that task success is what you get when you combine data with the right representation of your scene. And then there is what I would call the epiphenomenon view, which says that we should view scene understanding as an epiphenomenon or an emergent consequence of performing well at a sufficiently large variety of sufficiently complex tasks. So the epiphenomenon view essentially contradicts this way of looking at end-to-end training, and this is actually going to be the focus of my talk. There's an important caveat that I want to make here, though, which is that this view is predicated on the notion that tasks are broad and general enough. And we could argue that if the task is so general, like, for example, ImageNet classification or even some representation learning objectives, maybe those are, in fact, scene understanding tasks. And I think that's a very valid way of looking at it. The crucial distinction to me between the classic view and the epiphenomenon view is that the epiphenomenon view doesn't require us to select the representation ourselves. The representation of the scene, the way that understanding is represented, emerges naturally as a consequence of performing tasks. So what would it take to understand the world via end-to-end learning? There's one challenge with this, which is that the world is pretty complex. If we think about our universe, like, yes, it has galaxies, it has stars, it has physics, it has kind of the day-to-day complexity of objects we interact with, visually very complex scenes, other agents, and so on. It's tempting to imagine that if you just show a model enough pictures of our universe, it will actually learn to understand our universe. So you could, for instance, think about an image capturing model or a visual question answering model and consider how such a model might understand the world. And we've seen some examples where, for example, image capturing models can actually do a pretty decent job of learning some meaningful concepts. Like, for example, that this is a picture of a group of people standing around a room with remotes. But such models can also make some pretty silly mistakes. Like, for example, concluding that there's a toilet with a seat up in this picture where, of course, there's a bathroom without a toilet, or that this picture of a person in a furry coat is actually a teddy bear. I think part of the reason for these kinds of issues is that in fact the universe of the image capturing model or the visual question answering model or the image classification model doesn't quite match our universe. It looks like our universe, but its physics are different. In the image capturing universe, you see sequences of images one after the other with corresponding phrases, but you don't get the interaction, you don't get the physics, you don't get the action-response tuples. So I think that in order to get scene understanding to truly emerge from end-to-end learning, you need an embodied learning recipe, one where you have an agent that interacts with the world and observes the consequences of its actions, attempts to succeed at a variety of meaningful tasks, and from doing so, accomplishes some kind of understanding of the world. So what I'm going to talk about today are a number of projects that we've done that try to basically provide a little bit of evidence for this hypothesis. One of the things we have to select is what end-to-end task we're going to use. And remember that it is important which task we use. The tasks have to be broad and general enough to require meaningful understanding of the world. I'm going to talk about two broad categories of tasks. Model-free tasks, which you can think of as predicting future rewards, and model-based tasks, which you can think of as predicting future observations. Let's start with the model-free setup. I'm going to begin with a small experiment that we did at this point about 5 years ago, around 2015, to try to just understand how end-to-end learning might differ from explicit modeling of scenes. This is some work that was done together with Chelsea Finn, Trevor Darrell, and Peter Beal. It was actually done during my postdoc, where we wanted to get this PR2 robot to learn to insert a shape into a shape-sorting cube. So it was an autonomous training process. So here you can see the robot actually practicing putting in the shape-sorting cube, and it's supposed to learn to do this task from images. And then at test time, Chelsea could hold the shape-sorting cube in her hand, and the robot would figure out where it is and insert the shape. But one of the things we want to understand in this paper is whether the end-to-end training of these visuomotor skills was actually important for good performance. At the time, this was a very controversial question because at the time, most robotics researchers did not think that deep learning, much less deep reinforcement learning, was actually a viable strategy in robotics, so it was sort of up to us to demonstrate its value. So what we did is we set up a comparison where we train a model that just localizes the hole in the shape-sorting cube. And we could localize it with 1.3 centimeters of error, which compares well with kind of state-of-the-art methods at the time for monocular localization. But the tolerance on the shape in the shape-sorting cube was just a few millimeters. So this error by itself was actually too much to perform the task. It turned out that if you actually use the predicted pose to do the task, you would never succeed. If you use the features from that model, you would succeed sometimes, and if you train the whole model end-to-end, you would succeed almost all the time. The reason for this, of course, is that it's neither necessary nor sufficient to accurately localize the hole. The robot just needs to put the shape in. The vertical position matters a lot less. The horizontal position matters less if it uses a robust strategy. So the end-to-end learning could take advantage of these properties. It could perform just enough perception to do the task, whereas the modular approach could not. Now, of course, to really get an understanding of the scene, we need much broader tasks, much more general objectives, and much more data. So much more recently, back in 2018, we built a system called QT-Opt, which is a robotic learning system that essentially extends Q-learning, and its aim is to enable large-scale training of robotic manipulation skills from many robots collected over large periods of time. We applied this system to the task of robotic grasping. So we collected data from about 1,000 training objects, collected about 600,000 training grasp attempts, and then set up a deep convolutional neural network to represent the Q function with 1.2 million parameters. The only grasping specific feature in this whole system was actually the reward function, which was 1 if the robot grasped an object successfully. Now, I'm not going to go too much into the details of how this thing actually worked. What I want to talk about primarily is the kind of behaviors that end up emerging from this training process. Although the system was only trying to grasp objects, in the course of doing that, it actually acquired some pretty interesting behaviors. For example, here we're going to have a person actually perturb the robot, and you can see that it responds intelligently. It immediately goes in for another grasp. When it picks up some easy objects, it just grasps them right away. When it gets a difficult object like this round tennis ball, if the object gets knocked out of the gripper, it's sort of not confused by that. It actually repositions the hand and eventually picks up the object. When it tries to pick up a small, difficult object like this clothes hook, it's actually going to fail in the first attempt, but it's actually watching what happens, and it notices that when it fails, it needs to reposition the gripper and try again. This system can grasp objects in dense clutter, objects that are transparent, large, small, and so on. And in the process of doing this grasping, it does a lot of interesting things like probing objects, repositioning them, moving clutter out of the way, and so on. And it performs very well on a wide range of objects that it's never seen before. In fact, on a test set consisting of difficult, previously unseen objects, including small objects, large objects, soft objects, hard objects, and so on, it gets a success rate of 96%, which to my knowledge is basically the state of the art for grasping systems that have to grasp from monocular RGB images. Now, of course, this grasping system doesn't work all the time, so its understanding of the world is highly imperfect. But because it's trained with reinforcement learning, there's a very easy solution to this, which is to learn on the job. So let's say that during training, you trained your Q function, it has a success rate of 96%, but then at test time, it's tasked with picking up some glass bottles that are very difficult to grasp, and it has a success rate of 49%. With an ordinary computer vision system, we would be in a lot of trouble at this point. We'd have to collect more labeled data and retrain the whole thing. But with reinforcement learning, there's a very easy solution, which is to just keep training, because this system can supervise itself. There's no human effort required for this. In fact, there's actually no reason to turn off the training when the system is deployed. Every grasp that it collects is additional training data. So to evaluate this, we conducted an extensive empirical investigation where we started with our 600,000 initial trials, and then for each variant of the scene, we collected an additional 800 trials, corresponding to about 4 hours of data, to see how well the system could adapt. And you can see in this video performance after adaptation for a range of different perturbations. Grasping glass bottles that were very difficult for the system to pick up initially, grasping objects under very harsh lighting, which drastically changed the appearance of the scene, grasping objects with a checkerboard in the background, with a different gripper, and with a highly modified offset gripper by 10 centimeters. In fact, most of the performance of this fine-tuning process was actually acquired after the first 400 grasp attempts, which is about 2 hours of fine-tuning. Now, you might say that this is still not fully signaling an understanding of the scene because we're still testing this thing on its actual ability to grasp. So another thing that we've investigated, and this is work that was led by Eric Zhang and my student Colleen Devon, was whether we could actually acquire an understanding of object semantics, object identity, and object localization entirely through grasping. So this work is going to leverage a pretty simple insight, which is that if you grasp some object, like this blue bottle, that object must have been present in the scene before the grasp, and it must be absent in the scene after the grasp. We can leverage this idea by setting up a kind of arithmetic that we enforce on our representation. The representation of the scene before the grasp minus the representation after the grasp should be roughly equal to the representation of the object that was grasped. We can instantiate this like this. Let's take a convnet and use it to embed the scene, to produce an embedding, and we'll embed both the pre-grasp scene and the post-grasp scene, and then take their difference. And then we'll say that this difference should be close to the embedding of the object that was grasped. And we'll use a contrastive loss to enforce this similarity, so that the embedding of the same object is close to the difference, embeddings of other objects are far from the distance. Now, crucially, we're not going to use any ground truth knowledge of object identity. So if you picked up the blue bottle twice, you would actually repulse the second grasp from the difference in the first grasp. But because the negatives for this contrastive loss contain so many other images containing other objects, on average, it'll actually repulse other objects more than it will repulse the same object. One of the things we can do with this representation is perform object-specific grasping. So you're going to see an image pop up on the screen. The robot is tasked with picking up the object corresponding to that image, but crucially, the object in the scene doesn't look the same. It might be from a different viewpoint. It might be oriented differently. So here the object is tasked with picking up a brush. The brush in the scene looks nothing like the brush in the image. And of course, after it's picked up, it doesn't look the same either. But the robot still localizes it successfully. And crucially, these are test objects. These are not objects that the model was trained on. Besides picking up the correct object, the robot will also exhibit some interesting behavior to try to isolate that object from clutter. So occasionally it picks up a couple of things, but whenever it's able to, it'll actually move clutter out of the way in order to pick up just the right object. And this is very interesting because we didn't tell it to do this. This is emerging entirely from reinforcement learning and this contrastive objective. In fact, when we tested this system on its ability to pick up the right object on a test set of objects that were not seen during training, we found that our learned grasp-to-vec representation actually outperformed a model that was allowed access to true object labels during training. On the training objects, it performed about the same because the true labels contained a lot of information, but on test objects, it actually performed better. Furthermore, the representation learned by this system could actually give some pretty decent object localizations, despite never having been trained for localization. So what you're seeing in the middle image is a heat map of the convolutional layers for the images on the bottom, trying to find the feature vectors in the conv layer that are most similar to the features of the object at the top. So it's essentially taking the dot product of the objects at the top with each location in the image at the bottom. And you can see that it actually picks up on the location of that object in the scene. So this means that simply through this contrastive loss NRL, the method was able to essentially learn to understand scenes well enough to localize objects. The next question we're going to ask is whether we can use reinforcement learning to learn to understand open world scenarios, not just grasping in a laboratory, but outdoor scenes that are not under our control. So in these experiments, which were performed by my student Gregory Kahn, we trained this jackal robot to navigate around its environment. Data was collected entirely autonomously through random navigation, and then the robot was trained to predict whether a given sequence of actions might result in a bumpy ride, or whether a given sequence of actions might result in a collision. And what you're seeing in the animations at the bottom are predictions for different candidate action sequences, on the left for bumpiness, and on the right for collision. And you can see that in training this entirely self-supervised way, the robot is actually able to figure out bumpiness, so it's able to understand terrain properties, and it's able to understand the basics of geometry by being able to predict collisions. The training procedure for the system is pretty simple. We have a convolutional neural network with an LSTM layer in the middle. The LSTM reads in a sequence of candidate future actions, and then the model outputs a sequence of predictions about quantities of interest. So you can think of this as basically predicting candidate reward sequences, candidate bumpiness and candidate collisions. Now, one of the things we can try to understand is whether this system can then acquire some interesting navigational affordances. So here we're seeing our trained system navigating an outdoor field, a grassy field. On the left is a baseline that uses the LiDAR mounted on the jackal robot to try to understand the geometry of the scene and then navigate around that geometry. This baseline perceives the grass in the grassy field essentially as impassable obstacles, whereas our approach is able to correctly understand that grass is passable because it learned that through experience. So it learns a kind of navigational common sense that some obstacles are traversable and some aren't. I think this is very interesting to point out because a conventional geometric approach that just tries to reconstruct the geometry would not be able to acquire this behavior. Similarly, when driving outdoors on different paths, this method was able to figure out that concrete paths avoid bumpiness, whereas driving on the grass results in a more bumpy ride. All right. Now, in the second half of this talk, let me talk a little bit about model-based methods. In contrast to the model-free methods I described before, the model-based methods attempt to actually predict the full sequence of future observations. So you could imagine that we have our robots, it's interacted with the world and collected a collection of experience, which consists of states, actions, and next states, and then it's going to use this experience to learn to predict future states or future observations, and then occasionally collect more data to improve its performance. Once such a model has been trained, the robot can actually perform desired tasks simply by taking as input the user's task specification and then trying out different action sequences through its internal model and selecting the action sequence that leads to the desired outcome. So what I'm going to discuss is work that was covered in a number of papers, which are mentioned here on this slide. We need to first collect some data, and we're going to collect data essentially in much the same way that the children do by interacting with the world through play. So these robots are going to play with objects in their environment, randomly moving things around, collecting some experience, and then that experience will be used to train a predictive model, to train an understanding of the world. Here you can see some of the predictions from this predictive model. The two rows, each row shows predictions starting from the same initial image, but each column corresponds to a different action sequence. So you can see that for different action sequences, the robot's arm moves in different ways, and when that arm contacts objects, the objects also move in different ways. We can give the robot a task by selecting a point in the scene, indicated with a red dot, and indicating to the robot where that point should go, indicated with a green dot. So we can ask what the robot predicts, and here it correctly predicts that the stapler should move to the right. The heat map at the bottom shows the predicted movement of that red point. And when we execute that in the world, the robot correctly reaches out, grabs a stapler, and moves it to the desired location. These tasks may seem simple, but it's important to remember that they're performed entirely from images, only using this end-to-end model without any additional geometric knowledge or knowledge of objects. But perhaps more interestingly, we can actually then use the models like this to examine the robot's understanding of the world. One of the things we can try to do is we can see if the robot can learn automatically to use tools. So here, we're going to give the robot a task, which is to move these two objects, and there's a tool position in the image, and the robot is going to have to figure out that it has to pick up the tool and use it to slide both objects together, and then perform that in the environment. So in the middle, you can see the prediction, on the right, you can see the actual execution. To train such a model, we basically train the predictive model just like before, with one modification. We need to actually ensure that the robot can understand that tools exist and they can be used to move objects. So in addition to random data collection, we're also going to provide the robot with some number of demonstrations. Crucially, these demonstrations are not demonstrating the task that the robot will be asked to do at test time. It's still up to the robot to figure out how to do the task. The demonstrations are just showing that usage of tools is something that exists in the world and something that is available for it to use, but it'll have to figure out on its own how to actually use it. And then at test time, we'll actually use a derivative-free planning algorithm based on the cross-entropy method to plan through this model to perform the task. So here are a few examples of tool use tasks that this model could perform. Here we told the robot to move two objects down from the plate, and the robot figured out they could pick up the sponge and use the sponge to move these objects. Here we told the robot to move this blue object to the upper part of the bin, but we disallowed it from moving the gripper to reach out for the blue object. So the robot had to figure out on its own that it had to actually use this tool to move the blue object, so it's not permitted to move outside the green zone, and the robot was able to do this successfully. Here we have kind of an improvised tool use task, so the students left some of their junk out on the table, along with a bottle, and we asked it to move two pieces of garbage off to the side to clean up, and the robot figured out that it could pick up the bottle and use the bottle to sweep the garbage. And this is work that was done by Annie Shee, who's a student with Chelsea Finn, and Frederick Ebert, who's co-advised by myself and Chelsea. One thing we also wanted to make sure of is that this model could actually figure out that in some cases tools should be used, and in some cases they shouldn't. So here, we set up a task where the robot has to move two objects, and it was able to correctly figure out that it needs to use the tool to move both of these objects. But next we set up a task where there was only one object that needed to be moved, and here it's actually much quicker for the robot to simply move the single object, and that's in fact exactly what it does. So this shows that it's not simply copying tool use behavior it's seen before, it's really looking at the scene, trying to understand what sequence of actions will result in the desired outcome most efficiently, and then performing that sequence of actions. All right, so to conclude and summarize, I discussed an embodied learning recipe for scene understanding, a recipe where you can have an agent that interacts with the world, performs some tasks end-to-end, and these are primarily prediction tasks, predicting rewards and predicting future observations. And based on those tasks, actually acquires a representation of the environment that reflects some degree of understanding. And I talked about how we can probe this representation in various ways. For example, I discussed how we can learn behaviors from large amounts of interaction for things like grasping, and then have things like understanding of object position or even object identity emerge from these grasping skills. I talked about how we could train predictive models for collision and bumpiness and have robots that understand navigational affordances, like, for example, the fact that driving on concrete paths results in a less bumpy ride, or that grass in a grassy field does not constitute an impassable obstacle, whereas a wall does. And then I also talked about how building predictive models and training those predictive models end-to-end could result in robots that have some understanding of their environment to the point where they could use tools, reposition objects, and correctly understand situations where tool use is called for and situations where it isn't. I'd like to thank the students that were involved in this work, and I'd like to also thank all of you for listening. Thank you very much, and I'll be happy to take questions during the question period.